Good morning, everybody, and thank you to the Mandela Mining Precinct for giving me the opportunity to present this short lecture this morning. My name is Professor Francois Malan from the University of Pretoria. I've currently got a keen research interest in the design of board and pillar layouts, and today I'll present some of the research that was conducted on pillar strength formula. This work was part of the Mechanized Mining Systems program at SMRD, and it specifically looked at rock engineering guidelines for mechanized mining. Now, of course, the scope for such a rock engineering project is very large, and we had to limit it to the following 4 key items. And these are board and pillar layout designs, support design for mechanized mining. What is the effect if there's no blasting on the seismic patterns and numerical modeling techniques? And the methodology we followed in the project was, first of all, to have a comprehensive literature review on these methodologies for mechanization. Then we had a workshop with industry that was followed up by a questionnaire to industry as well, just to identify the gaps in knowledge. And out of that, the recommendations flowed for best practices and future work there. The literature survey was very valuable as we could identify the following gaps in knowledge. There's currently no accepted South African formula for pillar strength in the hard rock board and pillar mines. And it's actually critical that we actually understand this pillar strength a bit better, especially as these board and pillar layouts tend to become deeper in future. Secondly, there was no method to determine pillar strength when weak layers are present. And of course, this is a problem as well because we already had 3 major mine collapses in South Africa where these weak layers were present. In terms of support design, the empirical design charts for support selection is not applicable to South African rock conditions, not necessarily, because these are empirical techniques based on rock conditions in other countries. And the alternative for analytical support design, rock engineers often do not have enough knowledge on the key structures affecting stability. The 5th point, it is known that mining rate may affect seismicity. This has been known for many years in the gold mining industry, but it's very difficult to quantify because we haven't got the right constitutive models to simulate the rock behavior. Mechanization with no blasting may result in a higher seismic risk throughout the day, and we do need to understand this better if we start mechanizing the gold mines on a much larger scale. And then the last point, calibration of the numerical models is very difficult when inelastic constitutive models are used. An important component of this particular project was to investigate the effect of depth on extraction ratio in board and pillar mines. And to illustrate this effect, just consider a regular board and pillar layout, as I've illustrated here on the right. For that particular layout and pillar strength, assume a Headley and Grant power law formula given by the pillar strength, which I've indicated here on the slide. I've used that because it's very clear from the workshop and the questionnaires sent to the industry that most of the industry is still using this Canadian uranium formula, even though it came from that particular country. For these layouts, it's customary to design a factor of safety as well. And if all of that is plugged into the equation for extraction ratio, it can be shown that the extraction ratio is a simple decreasing linear function of depth given by this equation at the bottom, where gamma is given by all those various parameters. The equation on the previous slide was actually used to illustrate the effect of depth on extraction ratio. And what I'm plotting on this particular graph is extraction ratio on the y-axis versus depth below surface. And I've plotted 3 scenarios. You see 3 lines there, and that is plotted for different K values in the pillar strength formula. It's essentially the in situ rock mass strength. Now the red line, ideally, of course, we want an extraction ratio of 75% or higher in these Borden pillar layouts. And if the K value is very low, typically we're only going to get this extraction ratio up to a depth slightly more than 200 meters. If the rock mass strength is very high, the green line, K equals 90, then perhaps we can go as deep as 650 meters. But it's very clear from this particular graph that we need to understand the pillar strength much better to increase the extraction ratio as we go. Another problem we're facing is that we're not 100% sure what is the most appropriate pillar strength formula to use for our South African pillars. It's still very common to use the power law formula, as I've shown here on this slide. And it's actually useful to indicate what the effect is of pillar volume on pillar strength by just writing this equation in the alternative form, and that can be done. Look at these cubes. So we've got a pillar with a width of W and mining height of H. So the volume of that particular pillar is given by the equation shown there, and the width to height ratio is then just a function of the width to the height. And by making those assumptions, that power law formula can actually be rewritten in the more complex form given here at the bottom. And when plotting that particular formula, then normalize it with respect to K as a function of pillar volume, we get a very interesting behavior. If the exponent alpha is bigger than beta, as we've currently got with the Merensky formula that was derived some years ago in a Plattmine formula, we can actually see that the strength of the pillar actually increases with pillar volume. You can see those two cubes have got the same width to height ratio, but of course the volume of the one on the right is much higher, so this formula actually predicts that the strength of that pillar on the right is larger. If alpha, however, is smaller than beta, then we get the behavior at the bottom where as the pillar volume increases, the pillar actually becomes weaker. Both of these formula are currently being used in industry, and we actually need to determine what is the most appropriate. So to conclude then, what is the best way forward? Clearly, from the short presentation, we'll have to focus on efforts to determine pillar strength better in Borden pillar operations. And this will typically involve the following work: laboratory work. There's still the option of using a linear strength formula for these pillars, and we need to compare that with a power law formulation. Underground back analysis of small pillars is always very useful, because if these pillars are still intact, it gives us a very good indication of at least the minimum strength of these pillars, but we'll have to do it. It will have to be commodity specific and be done on a much larger scale than previously done. Underground experimental work to mine some of these pillars and induce failure. For example, there was a very nice experiment at Booysenstal to exactly do that, and that actually taught us a lot regarding the strength of these pillars. As I mentioned earlier in the presentation, weak layers can be very detrimental for pillar strength, and we need to understand this much better. And because it's such a large undertaking, a first step would in fact be a formal scoping of the project, and we need to answer questions like realistic timelines. We can't work on this problem for the next 20 years. What is the funding required? Is there enough laboratories in South Africa where we can do the laboratory testing? And underground, of course, a single test site is probably not going to be enough, and we need to do this in various areas. So there is my pillar story. Thank you very much for the opportunity to present this.